Have you ever wondered what might be happening in the vast, dark spaces between the stars, not just the planets and galaxies we can see, but the invisible, energetic phenomena constantly unfolding all around us? Every second, our planet is being subtly struck by powerful cosmic rays, mysterious particles traveling at nearly the speed of light, originating from some of the most extreme events in the universe. These aren't just random bits of energy, they're messengers carrying secrets from supernova explosions, active black holes, and regions of space we still don't fully understand. And yet, despite their constant presence, many of these cosmic rays remain one of the greatest enigmas in modern astrophysics. As we begin this journey together, picture yourself not just as a viewer, but as an investigator stepping into a cosmic detective story spanning billions of light years. Some of these particles arrive with energies so tremendous that they defy our current understanding of physics, energies far beyond what our most powerful particle accelerators can produce. Where do they come from? How are they accelerated to such incredible speeds? And what can they teach us about the universe's most violent and mysterious phenomena? For decades, scientists worldwide have been captivated by these questions, tracing the paths of these elusive particles back through space and time, often ending with more mysteries than answers. In this video, we'll explore the top 25 most enigmatic cosmic rays ever detected, each with its own story, its own extraordinary energy signature, and its own tantalizing clues about the cosmos. From events that might be tied to colliding galaxies to particles that seem to challenge the very laws of physics, we're about to dive into a world where every detection raises new questions and opens new possibilities. This isn't just a list, it's an invitation to witness the edge of human knowledge and curiosity. So settle in, open your mind, and get ready to see the universe in a whole new light. To kick off our list, we encounter a particle so extraordinary, its very detection forced physicists to rethink the limits of the possible. This is the story of the Oh My God particle. On the 15th of October 1991, a solitary subatomic particle, most likely a proton, screamed into Earth's atmosphere over the Utah desert. It was not like any other cosmic ray. It was moving at an unimaginable 0.999999999999996 times the speed of light. To put that incomprehensible energy into perspective, it carried the kinetic energy of a baseball hurled at nearly 100 kilometers an hour, but compressed into a single, infinitesimal speck of matter. This was the energy equivalent of dropping a brick on your foot from waist height, but that brick was a fundamental particle smaller than an atom. The detector that captured this event, the University of Utah's Fly's Eye experiment, recorded an air shower of secondary particles so vast and energetic that researchers initially struggled to believe their own data. The numbers were checked and rechecked, but they held firm. This one particle hit with an energy of about 320 exa-electronvolts. That's a 3 followed by 20 zeros. This energy level is tens of millions of times more powerful than anything we can create in our most advanced human-built particle accelerators, like the Large Hadron Collider. And this is where the mystery deepens into a profound cosmic conundrum. According to our best models of physics, a particle with that much energy should not be able to travel very far through the universe. It should constantly lose energy by interacting with the cosmic microwave background radiation, the faint afterglow of the Big Bang that permeates all of space. This is known as the Greisen-Zatsepin-Kuzmin, or GZK, cutoff. It's a theoretical limit on how far ultra-high-energy cosmic rays can travel. The existence of the Oh My God particle, then, presents a monumental puzzle. If it came from a distant source outside our galaxy, it should have been slowed down long before it ever reached us. So, did it come from somewhere relatively close by within our own Milky Way? The problem is, we simply cannot find any known object within our galaxy that could possibly act as such a powerful natural accelerator. Even the most violent and energetic phenomena we know of, like the supermassive black hole at our galaxy's heart or the remnants of a supernova explosion, seem incapable of producing such an absurd amount of energy. It's as if a single pebble was fired from a slingshot with the force of a nuclear explosion. The known mechanisms just don't account for it. This single detection, now over 3 decades old, remains the gold standard for extreme energy. It is a ghost from the cosmos, a persistent reminder that the universe still holds secrets about its most fundamental operations and the existence of cosmic engines of unimaginable power that we have yet to even conceive of. Yet mere decades after the Oh My God particle redefined the limits of extreme energy, another event occurred that was not merely a repetition but an escalation of the mystery. In May of 2021, the same patch of Utah sky that delivered that legendary particle witnessed the arrival of another cosmic ray of almost incomprehensible power. Detected by the Telescope Array project, this particle carried an energy exceeding 240 exa-electronvolts. In a tradition of giving profoundly mysterious cosmic events equally profound names, the scientists dubbed it the Amaterasu Particle, after the powerful Japanese sun goddess who is said to have brought light to the world. It was a fitting name for a particle that brought not light but a new level of cosmic confusion. The sheer power of Amaterasu is staggering enough, but the real enigma lies in its origin. When researchers traced its incoming path back through the cosmos, hoping to find a source worthy of such a particle, the trail led them to nothing. It pointed back to a vast, empty region of space on the outskirts of our local void, a desolate area between constellations with no bright galaxies, no active black holes, no supernova remnants, none of the usual suspects we would blame for such a violent event. It's the cosmic equivalent of hearing a deafening explosion right next to you, spinning around and finding yourself completely alone in an empty field. This void origin forces us to confront some deeply unsettling possibilities. Perhaps our understanding of how these ultra-high energy particles travel through the universe is fundamentally flawed. Could incredibly powerful and invisible magnetic fields scattered throughout intergalactic space be bending the paths of these particles so severely that they appear to come from nowhere, effectively erasing their true origin point from our maps? Or is there an entirely new, unknown astrophysical process at work in these so-called empty spaces, a hidden engine capable of launching particles with forces we cannot yet comprehend? The Amaterasu particle doesn't just add to the mystery, it reinforces a pattern that is both thrilling and humbling for science. These detections are not flukes, they are signposts pointing toward gaps in our knowledge. They tell us that our catalogue of the universe's most energetic phenomena is still incomplete. Each one is a clarion call for the next generation of observatories, like the planned expansion of the Telescope Array, which will give us a finer net to cast into the cosmic deep. We are being shown that the greatest cosmic accelerators are out there, hiding in plain sight, and we are only just beginning to learn how to see them. But while particles like Amaterasu seem to arrive from the deepest voids of intergalactic space, not every enigmatic cosmic ray comes from such incomprehensible distances. In fact, some of the most telling messengers originate right on our solar system's doorstep, from the turbulent boundary where our sun's influence finally wanes. These are the anomalous cosmic rays, and their story is not one of unimaginable power, but of delicate processes occurring in the thin, magnetic shell that separates our home from the galaxy at large. To understand them, we first need to journey to the edge of our solar system, to a region known as the heliopause. This is not a solid wall, but a vast dynamic boundary layer where the outward pressure of the solar wind, a constant stream of charged particles flowing from the sun, finally equals the inward pressure of the interstellar medium, the thin soup of gas and dust that fills the space between stars. Imagine it as the point where a river of plasma from our Sun flows into the ocean of the galaxy, creating a complex zone of mixing and turbulence. It is here, in this cosmic liminal space, that anomalous cosmic rays are born. The process begins with neutral atoms from the interstellar medium drifting into our solar system. Unlike charged particles, these neutrals are unaffected by magnetic fields and can sail right through the solar wind. As they approach the Sun, however, many of these atoms have their electrons stripped away by solar ultraviolet radiation or through charge exchange collisions with the solar wind itself. Suddenly transformed into positively charged ions, they are no longer free travelers. They become caught in the flow of the solar wind and are unceremoniously dragged back out towards the heliopause. This is where the magic happens. At the heliopause, the chaotic motions of the plasma and the shock waves present there can act as a natural particle accelerator, albeit a far gentler one than a supernova remnant. These newly created ions get caught in these magnetic structures and are accelerated to modest energies not enough to rival the oh my god particle, but enough to earn them the title of cosmic rays. Once energized, they can then diffuse back inwards toward the inner solar system and our detectors. What makes them anomalous is their distinct composition. They are predominantly elements like hydrogen, helium, oxygen, nitrogen, and neon, which are abundant in the local interstellar medium, but are relatively rare in the standard population of galactic cosmic rays. So, while they may lack the jaw-dropping energy of their ultra-high-energy cousins, their value is immeasurable. They act as tiny probes, literally sampling the material from just beyond our solar system. By studying their composition and flux, scientists can indirectly analyze the makeup of the local interstellar cloud through which our Sun is moving. Furthermore, because their journey is tied to the structure of the heliosphere, they serve as a powerful diagnostic tool. Changes in the intensity and direction of these anomalous cosmic rays help researchers map the shape and dynamics of the heliopause itself, revealing how this protective bubble breathes and shifts in response to changes in solar activity. They are a reminder that even the boundary of our own solar system, a region we are now only beginning to explore with spacecraft like Voyager and IBEX, holds profound mysteries about our place in the galactic environment. But if the anomalous cosmic rays give us a window into our local interstellar neighborhood, then the particles we're about to discuss seem to defy the very rules of intergalactic travel. This brings us to one of the most profound theoretical boundaries in all of cosmic ray physics, the Greisen-Zatzeping Kuzmin cutoff. Proposed in the 1960s, the GZK cutoff isn't just a random line in the sand. It's a fundamental prediction based on the well-established laws of physics. It states that any proton traveling across the universe with an energy greater than about 50 exa-electronvolts should not be able to reach Earth. The reason lies in the cold, sparse glow that fills every cubic centimeter of the cosmos, the cosmic microwave background radiation. This background radiation is the faded remnant of the Big Bang, a bath of low-energy photons that has been cooling for over 13 billion years. For a cosmic ray proton traveling at near light speed, however, these photons are not just a faint whisper from the past. They appear dramatically energized due to relativity, an effect known as blue shifting. From the proton's perspective, these microwave photons are transformed into potent beams of gamma-ray light. When such a high-energy proton inevitably collides with one of these blue-shifted photons, it triggers a reaction that robs the proton of its energy, producing other particles in the process. Over millions of light-years, this process acts like a kind of cosmic friction, relentlessly sapping the energy of the most powerful protons until they fall below the GZK threshold. It effectively creates an immense, invisible barrier around our galaxy, a barrier that ultra-high-energy cosmic rays should not be able to cross, and yet they do. We've already met two spectacular violators of this rule, the Oh My God and Amaterasu particles, but they are not alone. detectors like the Pierre-Auger Observatory have recorded multiple events with energies clearly sailing past this theoretical limit. Each detection is a direct challenge to our understanding. If the GZK process is correct, as our models insist it should be, then these particles must have originated from somewhere relatively close by within our local group of galaxies, a region about 3 million light-years across. The logic is inescapable. They couldn't have come from farther away without losing their energy. This should make them easier to trace back to a source, but just like with Amaterasu, the search often leads to a frustrating blank spot in the sky, devoid of any known object capable of such incredible acceleration. This contradiction has forced astrophysicists to consider some truly radical possibilities. Perhaps our comprehension of the GZK process itself is incomplete. Maybe the distribution of the cosmic microwave background is not as uniform as we believe, or the interactions are more complex than our models account for. Another intriguing idea is that these are not protons at all, but something entirely different. Could they be heavier atomic nuclei like iron, which interact with the background radiation in a slightly different way? Or are they perhaps exotic, unknown particles that lie outside the standard model of particle physics, particles that simply don't play by the same rules, like theoretical super-heavy dark matter particles annihilating in the distant universe? Each violation of the GZK cutoff is more than just an anomaly. It is a potential key to unlocking a deeper layer of reality. They push us to question not only our maps of the universe, but the very physical laws we use to read them. These ultra-high-energy messengers are insisting that something is missing from our picture, whether it's a new type of astrophysical object lurking in nearby intergalactic space, a flaw in our most fundamental theories, or a doorway into physics that operates at energies we can only dream of recreating on Earth. They represent a frontier where observation stubbornly refuses to match prediction, and that is exactly where the next great discovery is always waiting to be found. Yet for all the mystery surrounding the origins of the most extreme particles, some cosmic rays carry with them a return address, stamped by the most violent and brilliant events in the cosmos. We now turn to a phenomenon that serves as a potential cosmic ray factory, an engine of destruction so powerful it can outshine an entire galaxy for a few fleeting moments. This is the story of cosmic rays born from gamma-ray bursts. Imagine the final cataclysmic moments of a truly massive star, many times heavier than our Sun. Having burned through its nuclear fuel, its core can no longer support its own immense weight. In a fraction of a second, the core collapses, giving birth to a newborn black hole or an ultra-dense neutron star. What follows is anything but quiet. Vast jets of plasma, hotter and more energetic than anything else we can conceive, are launched from the stellar corpse at speeds approaching 99.99% the speed of light. These jets, focused like laser beams, punch their way out through the outer layers of the dying star. When one of these jets is pointed directly at Earth, we witness a gamma-ray burst, a spectacular flash of the highest energy light in the universe, delivering in just a few seconds more energy than our Sun will emit across its entire 10 billion-year lifetime. It is within these relativistic jets that physicists believe a special breed of cosmic ray is forged. The mechanism is one of unimaginable violence and perfect conditions. As the jet blasts through space, it doesn't move as a smooth, uniform stream. Faster material at the rear end can plow into slower material ahead of it, creating massive shock waves. But these are not ordinary shocks like a sonic boom. These are relativistic shocks propagating through an environment where the laws of Einstein's special relativity dominate. In this extreme environment, charged particles, protons, and atomic nuclei can become trapped between magnetic fields on either side of the shock front. Each time they cross the shock, they gain a tremendous boost of energy, much like a tennis ball being slammed back and forth between two rackets moving at nearly the speed of light. This process, known as Fermi acceleration, can repeatedly sling particles until they are energized to levels that rival the most powerful cosmic rays we detect. The tantalizing link between these bursts and cosmic rays isn't just theoretical. We have observed compelling circumstantial evidence. In 2013, the Ice Cube Neutrino Observatory at the South Pole detected a pair of high-energy neutrinos, ghostly particles that rarely interact with matter, that arrived at Earth from a direction coinciding with a powerful gamma-ray burst. This is a crucial piece of the puzzle. Neutrinos are a direct byproduct of the same particle acceleration process thought to create cosmic rays. When a proton is accelerated within a GRB jet and then collides with another particle, it can produce not only gamma rays but also these elusive neutrinos. Their detection in tandem with a gamma ray burst is like finding smoke at the scene of a fire. It strongly suggests that protons are indeed being accelerated to cosmic ray energies within these stellar explosions. Connecting these distant blasts to the particles that strike our atmosphere revolutionizes our understanding of both phenomena. It suggests that gamma-ray bursts, these fleeting cosmic beacons, could be responsible for accelerating a significant fraction of the high-energy cosmic rays that permeate our galaxy and beyond. Each time we detect a cosmic ray that can be traced back to a burst, we are effectively collecting a piece of shrapnel from the explosive death of a massive star and the violent birth of a black hole. They offer a unique physical sample from an event that occurred billions of light years away, allowing us to study the inner workings of these extreme accelerators in a way that light alone cannot provide. By analyzing these particles, we can begin to decipher the physics of the relativistic shocks themselves, testing our models of how nature can harness such raw power to launch fundamental bits of matter across the universe. If the journey of a cosmic ray were a story, its energy would be the plot dictating its origin, its adventures across the cosmos, and ultimately how it ends. And just like any great story, the plot of the cosmic ray saga has two major twists, two unexpected turns in the narrative that have kept scientists guessing for decades. These are known as the knee and the ankle, not parts of the body, but peculiar bends or features in the graph that plots the number of cosmic rays we detect against their energy. It's in these subtle curves that we find vital clues about where these particles come from and the incredible journeys they undertake to reach us. The first of these plot twists is called the knee. As we move up the energy scale, the number of cosmic rays we detect steadily drops. More energetic particles are far rarer than their lower energy cousins. But around 1 million billion electron volts, or 10 to the power of 15 eV, this decline suddenly becomes much steeper. If you look at the graph, the line takes a sharp bend downward, much like the flex of a knee. For a long time, this was seen as a critical clue. The most accepted theory suggests that the knee marks an energy limit for cosmic rays confined within our own galaxy. The idea is that the Milky Way is permeated by a magnetic field, which acts like a vast, invisible magnetic cage. Lower energy particles get trapped in this cage, bouncing around for millions of years, which is why we see so many of them. But particles accelerated beyond a certain energy, the energy of the knee, are simply too powerful to be contained. They punch through the galactic magnetic field and escape into intergalactic space, which is why their numbers plummet so dramatically. The knee, then, was thought to be the dividing line between cosmic rays that are homegrown in our galaxy and those that come from beyond. But the story is never that simple. Decades of meticulous data collection from sophisticated ground-based arrays like the Cascade Grand Experiment in Germany have revealed a far more complex picture. Instead of a single clean knee, the data suggests the structure might be more nuanced, with multiple subtle knees and bumps for different types of cosmic rays like protons or ion nuclei. This complexity points not to a single escape mechanism, but to the intricate physics of how different particles are accelerated and how they propagate through the turbulent magnetic environment of the galaxy. The knee may not be a simple exit sign, but a fingerprint of the acceleration limits of specific sources within the Milky Way, like supernova remnants, whose shock waves might only be capable of pushing particles to these energies before they lose their grip. As we push our investigation to even more staggering energies, we encounter the second great plot twist, the ankle. This feature occurs around 1 quintillion electronvolts, or 10 to the power of 18 eV. Here, the spectrum does another about-face. The steep decline we saw after the knee actually flattens out again. The line on the graph curves upward, resembling the shape of an ankle. This is a clear signal that a new population of cosmic rays is beginning to dominate. While the particles below the knee are likely galactic, the prevailing theory is that the ankle marks the point where extragalactic cosmic rays take over. These are the true intergalactic travelers, the ones born in cataclysms far outside our Milky Way, in active galactic nuclei colliding galaxies, or perhaps the same gamma-ray bursts we discussed earlier. Their immense energy allows them to travel across millions of light-years of intergalactic space and still arrive at our doorstep with enough power to be detected. Yet, even this elegant explanation is hotly debated. Some models propose that the ankle isn't the start of the extragalactic population, but rather a dip caused by the energy loss of these very same extragalactic particles as they interact with the cosmic microwave background, an echo of the GZK effect we explored before. Other theories suggest a more complex mix, where both galactic and extragalactic sources contribute across a wide range of energies, with the ankle representing a complex transition zone rather than a clean handoff. Decades after their discovery, the knee and the ankle remain central mysteries. They are not merely data points on a chart. They are the direct signatures of the universe's most powerful particle accelerators and the magnetic labyrinths these particles must navigate. Unraveling their exact meaning is like trying to decipher a complex cosmic language. Each new experiment, each more precise measurement of these spectral features, brings us closer to understanding the fundamental question: how does the universe organize the production and distribution of these energetic particles? The bends in the spectrum are the keys to mapping the invisible architecture of the cosmos itself. So far, we've followed the journeys of solitary protons, the most common cosmic ray particles. But the cosmic rain falling on Earth is far more diverse, consisting of an entire periodic table of elements hurtling through space. This brings us to a fascinating and heavy class of travelers, cosmic rays composed of fully stripped atomic nuclei, from helium and carbon all the way up to iron and beyond. These aren't just simple protons, they are the intact cores of atoms, carrying a much greater electric charge and mass. This fundamental difference makes them powerful forensic tools, as each heavy nucleus carries a unique fingerprint that can be traced back to the specific cosmic environment that created and launched it. The very existence of these heavy particles tells a dramatic story. An atomic nucleus is a tightly bound collection of protons and neutrons, and it takes an enormous amount of energy to not only accelerate such a bulky object to near light speed, but to also first strip it completely of all its electrons. This violent stripping and acceleration points to truly extreme environments. The prime suspects are the expanding shock waves of supernova remnants. As a colossal blast wave from a stellar explosion plows through surrounding gas and dust, it can sweep up and accelerate not just individual protons, but also the heavier atoms present in the stellar debris or the interstellar medium itself. The heavier the element, the more it can be pushed by the magnetic fields in the shock wave, potentially allowing it to reach incredible energies. But the composition of these heavy cosmic rays holds even more specific clues. When scientists compare the relative abundance of elements in the cosmic ray flux to the natural composition found in our solar system, they find intriguing anomalies. For instance, elements like neon, magnesium, silicon, and especially iron are far more common in cosmic rays than their standard cosmic abundance would suggest. This isn't a random distribution, it's a signature. This overabundance points directly to sites where massive stars live and die. Wolf-Rayet stars, for example, are incredibly massive, hot stars that shed their outer layers in powerful winds laced with heavy elements forged in their cores. The material from these winds, rich in carbon, oxygen, and nitrogen, could be directly injected into and accelerated by surrounding supernova shock waves. The anomalous ratios we detect are therefore a direct sample of the processed material from these stellar giants. To read these elemental fingerprints, scientists use incredibly precise instruments stationed above the distorting effects of Earth's atmosphere. The premier tool for this detective work is the alpha magnetic spectrometer, a state-of-the-art particle physics detector mounted on the International Space Station. Unlike ground-based arrays that observe the secondary shower of particles, AMS observes the primary cosmic rays directly in space. It uses a powerful magnet to bend the path of incoming charged particles. The degree to which a particle's path curves in the magnetic field reveals its charge and momentum, allowing researchers to precisely identify its identity, whether it's a proton, a nucleus of oxygen, or a nucleus of iron. By collecting millions of these events, AMS builds an incredibly detailed census of the cosmic rays passing near Earth. This data is revolutionizing our understanding. By meticulously measuring the fluxes of different elements and even their isotopes, AMS and other experiments are not just confirming that supernova remnants are likely sources. They are beginning to pinpoint the specific types of supernova and the ages of the remnants involved. The heavy nuclei are messengers that tell us about the temperature and density of the material within the accelerating shock wave, and even how long the particles have been traveling through the galaxy based on the minute decay of certain radioactive isotopes. Each heavy nucleus is a tiny piece of cosmic shrapnel, and by assembling the pieces, we are slowly reverse engineering the workings of the most powerful particle accelerators in the Milky Way, building a periodic table of cosmic destruction and creation. For over a century, one of the most compelling questions in astrophysics has been a seemingly simple one. Where do the cosmic rays constantly raining down on Earth actually come from? While we've discovered particles that seem to arrive from the deepest voids and the most violent extragalactic bursts, the vast majority of the cosmic rays we detect, particularly those at lower and medium energies, are believed to be homegrown, born right here within the confines of our own Milky Way galaxy. And for decades, the prime suspect, the galaxy's foremost natural particle accelerator, has been the spectacular aftermath of a dying star, a supernova remnant. The theory is both powerful and elegant. When a massive star ends its life in a supernova explosion, it doesn't just fade quietly into the night. It unleashes a cataclysm of almost unimaginable force, ejecting its outer layers into space at thousands of kilometers per second. This creates a colossal, expanding spherical shock wave, a vast shell of hot gas and debris that plows through the surrounding interstellar medium for thousands of years. It is within this chaotic, turbulent frontier that the magic of particle acceleration is thought to occur through a process known as diffusive shock acceleration, often called Fermi acceleration after the physicist who first proposed the mechanism. Imagine this shock wave as an immense, moving wall. Ahead of it, the interstellar medium is peppered with magnetic fields and stray charged particles. As this wall of plasma sweeps forward, it doesn't just push material aside, it can trap particles within its magnetic structure. A single proton might cross from the turbulent region behind the shock to the calmer region ahead, only to be caught by the magnetic fields and flung back across the shock front again. Each time it makes this round trip, it gains a significant boost of energy, much like a surfer being pushed repeatedly by a powerful wave. Over many cycles, this process can accelerate particles from ordinary thermal energies to the tremendous velocities we associate with cosmic rays, effectively turning the entire supernova remnant into a gigantic natural particle collider. But a compelling theory requires solid evidence, and that is where modern astronomy has delivered some of its most stunning confirmations. We cannot see the cosmic rays themselves from across the galaxy, but we can see the brilliant, high-energy light they produce. When these accelerated particles, primarily protons, collide with the cool, dense gas of the interstellar medium, they produce pions, short-lived subatomic particles that almost immediately decay into gamma rays. This creates a distinct and detectable glow of very high-energy photons. Telescopes like the Fermi Gamma Ray Space Telescope and ground-based arrays like HESS and Veritas have scanned the skies for this specific signature, and they have found it. In historic remnants like Tycho's supernova, the site of a famous stellar explosion observed in 1572, and Cassiopeia A, the dusty wreckage of a star that died around 1680, astronomers have mapped a bright, shell-like structure of gamma-ray emission that perfectly aligns with the expanding shock front. This is considered the smoking gun, the telltale sign that protons are being accelerated to cosmic ray energies within these stellar graves. However, the story is not without its complications and ongoing debates. Not every supernova remnant shows this clear and powerful gamma-ray signal. Some appear dim and inefficient, which has led scientists to investigate why. The efficiency of a remnant as a cosmic ray factory seems to depend heavily on its environment and its age. A remnant expanding into a uniform, dense cloud of interstellar gas provides far more target material for particle collisions, lighting up brightly in gamma rays. In contrast, a remnant blowing a bubble in a more tenuous region of space might have little to push against, producing a much fainter signal. The age of the remnant is also critical. The acceleration is most potent during the free expansion phase, which can last for hundreds of years. As the remnant slows down and enters the later Sedov-Taylor phase, its ability to accelerate particles may wane. Furthermore, the complex structure of magnetic fields around the shock is crucial. If the fields are too weak or disorganized, particles can escape before being boosted to high energies. These complexities don't invalidate the theory, they refine it. They tell us that while supernova remnants are undoubtedly one of the galaxy's primary engines for cosmic rays, they are not all created equal. Their effectiveness is a delicate dance of timing, location, and magnetic conditions. The cosmic rays that eventually escape these accelerators and travel across the galaxy to our detectors are more than just random particles, they are cosmic fossils. They preserve the energy and the elemental fingerprints of those ancient stellar explosions, carrying within them the story of the violent events that not only seed galaxies with heavy elements, but also energize the interstellar medium and influence the very cycle of star birth and death itself. Each one is a tangible piece of a star's final, magnificent act. For years, the search for the origins of the most energetic cosmic rays was like trying to find a single screaming voice in a hurricane. The particles seemed to arrive from every direction with equal probability, a perfectly uniform and maddeningly anonymous drizzle. But as our detectors grew larger and our datasets more vast, a faint signal began to emerge from the noise. We discovered that the universe's most powerful particles are not arriving completely at random. There is a pattern, a subtle but statistically significant directional bias in their arrival. This phenomenon is known as anisotropy, and for ultra-high-energy cosmic rays, it is the first real clue pointing back to their celestial sources. The premier instrument in this detective work is the Pierre Auger Observatory in Argentina, a sprawling array of over 1,600 water tank detectors covering an area of 3,000 square kilometers, a landscape-sized instrument designed to catch the rare air showers from the most energetic events. By analyzing the timing of when these showers hit different detectors, the observatory can reconstruct the incoming direction of the original cosmic ray with remarkable precision. After years of collecting data, the scientists at Auger made a monumental announcement. the very highest energy cosmic rays, those above about 59 exa-electronvolts, do not show a perfectly uniform sky. Instead, they exhibit a large-scale anisotropy. Their directions are correlated with the positions of nearby active galactic nuclei and starburst galaxies. An active galactic nucleus is essentially a supermassive black hole at the center of a galaxy that is actively devouring vast amounts of material. As matter spirals into the black hole's insatiable gravity well, it heats up to tremendous temperatures and can launch jets of plasma and radiation across intergalactic space. These jets are prime candidates for the powerful accelerators we've been searching for. Starburst galaxies, on the other hand, are not defined by a single central monster but by a frenzy of collective violence. These are galaxies undergoing an extreme burst of star formation, leading to an epidemic of supernova explosions. The combined shock fronts from these frequent stellar deaths could create a widespread accelerator capable of pushing particles to incredible energies. The Augur data suggests that the ultra-high-energy cosmic rays washing over our planet are more likely to have begun their journeys in such extreme environments relatively close to home, within a few 100 million light-years of Earth. However, reading this cosmic map is not as simple as drawing a straight line back to a bright galaxy. The journey of a charged particle across millions of light-years is anything but a straight shot. Our galaxy, and indeed all of space, is threaded with magnetic fields. These fields, though incredibly weak compared to a common refrigerator magnet, are pervasive. As a proton or an atomic nucleus travels through these fields, its path is bent. The amount of deflection depends on two key factors: the particle's charge and its energy. A high-energy proton will be bent less than a lower-energy one, and a fully stripped iron nucleus with its 26 times the charge of a proton will be bent significantly more. This means that by the time a cosmic ray reaches us, its direction of arrival may be dozens of degrees away from its true source. It's the ultimate cosmic curveball. The particle's trajectory has been scrambled by the magnetic labyrinths of intergalactic space and then twisted again by the magnetic field of our own Milky Way. This is why a particle might appear to come from a seemingly empty patch of sky. We are seeing the end of a long and winding road, not the starting point. This magnetic bending is not just a frustrating obstacle, it is also a unique tool. By studying the patterns of anisotropy, how the particles are clustered and distributed across the sky, scientists can actually learn about the magnetic fields themselves. The slight deviations in arrival directions give us indirect clues about the strength and structure of the magnetic fields that fill the vast voids between galaxies, a property of the universe that is incredibly difficult to measure by any other means. The cosmic rays are acting as probes, and their slight directional biases are painting a picture of the invisible magnetic architecture of the cosmos. The large-scale anisotropy detected by the Pierre Auger Observatory is therefore much more than a simple pointer to a source. It is a complex cryptographic message that contains information about both the accelerator and the medium through which the particle traveled. Deciphering this message is a monumental task in cosmic tomography, requiring intricate computer models that simulate the propagation of billions of particles through known and hypothesized magnetic fields to see which scenarios match the observed sky. Each new ultra-high-energy event adds another data point, another brushstroke to this emerging map of extreme energy. It confirms that we are not just collecting random fragments of violence, but pieces of a structured, anisotropic universe where the most energetic particles are guided by invisible forces from their powerful extragalactic sources all the way to our detectors on Earth. But while we trace the paths of protons and atomic nuclei across the cosmos, there is another, even more elusive component of the cosmic ray shower that has delivered one of the most tantalizing puzzles of the 21st century. This mystery doesn't involve ordinary matter, but rather its strange and fleeting mirror image, antimatter. Specifically, we are talking about positrons, the antimatter counterparts of electrons. According to our standard models of cosmic ray physics, we should only see a tiny, dwindling number of these positrons at higher energies, but that is not what our detectors have found. Instead, they have recorded a startling and persistent surplus, an unexpected excess that rises with energy, defying conventional explanation and pointing toward phenomena that could reshape fundamental physics. This cosmic conundrum began to fully reveal itself with data from a series of sophisticated space-borne experiments. The Payload for Antimatter-Matter Exploration and Light Nuclei Astrophysics, or PAMELA, satellite, which operated from 2006 until 2016, was the first to report the anomaly with high significance. But it was the Alpha Magnetic Spectrometer, that incredibly precise particle detector mounted on the International Space Station, that confirmed the excess with breathtaking precision. AMS has collected billions of cosmic ray events, and its data paints a clear and baffling picture. The ratio of positrons to electrons in the cosmic ray flux does not fall off as energy increases, as traditional models predicted. Instead, it rises steadily from about 10 gigaelectronvolts upward, peaking around 300 gigaelectronvolts before perhaps starting a very gradual decline. This is profoundly counterintuitive. In the standard paradigm, the positrons we detect are not primary particles accelerated at a source. They are secondary products created when primary protons and nuclei collide with interstellar gas and produce pairs of particles and antiparticles. These secondary positrons should lose their numbers quickly as energy climbs, but the data shows the opposite trend. Something is injecting a fresh supply of high-energy positrons into the galaxy, and we have to figure out what that source is. This discrepancy has ignited a fierce and exciting debate in the astrophysics community, primarily centered around two compelling yet very different explanations. The first theory points to a known, though spectacular, astrophysical object, a pulsar. These rapidly spinning, ultra-dense neutron stars are the leftover cores of supernova explosions, acting as powerful lighthouses beaming radiation across the galaxy. A pulsar's immense magnetic field and rapid spin can generate tremendous electric fields, capable of pulling particles from its surface and accelerating them to relativistic energies. In this environment, electrons can be accelerated to such high energies that when they radiate light, that light can spontaneously transform into a particle-antiparticle pair, an electron and a positron. A nearby pulsar could therefore be flooding our local region of the galaxy with a wind of these freshly minted high-energy positrons, creating the excess that MS observes. The challenge with this theory is that it requires one or more pulsars to be located at just the right distance and orientation to Earth to account for the precise energy spectrum we see. While there are candidates like the Geminga pulsar, the match is not yet perfect, leaving room for doubt and for an even more exotic possibility. The second, and far more thrilling, explanation is that we are seeing indirect evidence for the annihilation of dark matter. This theory proposes that the universe is filled with a mysterious, invisible form of matter that outweighs normal matter by a factor of 5 to 1. While we can see its gravitational effects, we have no idea what it's made of. Many theoretical models suggest that dark matter could be composed of weakly interacting massive particles, or WIMP. If these WIMP are their own antiparticles, then when two of them collide, they could annihilate each other in a flash of energy, producing a shower of standard model particles, including pairs of electrons and positrons. The energy spectrum of the positron excess observed by MS could potentially be the signature of dark matter particles with a specific mass annihilating in the halo of our galaxy. The gradual rise and peak of the excess would correspond directly to the mass of the dark matter particle involved. This is why the positron excess has caused such a stir. It could be our first tangible glimpse into the hidden 85% of the matter in the universe. The controversy lies in distinguishing between these two scenarios. The dark matter interpretation is incredibly seductive, but the pulsar explanation is more conventional and requires no new physics. Current measurements, while precise, cannot yet definitively rule one out in favor of the other. Researchers are looking for additional clues, such as a sharp cutoff in the spectrum at very high energies that would be a telltale sign of a dark matter particle's specific mass, or a specific pattern in the arrival directions of the positrons that might point back to a nearby pulsar. What makes this anomaly so powerful is that it forces us to confront the limits of our understanding. Whether the source is a previously underestimated astrophysical engine or a profound discovery in particle physics, the positron excess is a clear signal that our standard model of cosmic ray propagation is incomplete. These antimatter particles are messengers from the dark, and they are insisting that we are missing a major piece of the cosmic puzzle, a phenomenon of either immense power or profound significance happening in the space around us. Yet for all the theoretical promise and tantalizing hints, the hunt for a definitive dark matter signature in cosmic rays remains one of the most formidable challenges in modern science. The central obstacle is a classic case of cosmic confusion. The signals we are searching for look almost identical to the background noise from known astrophysical processes. A pulsar and an annihilating dark matter particle can both produce a similar excess of positrons. The gamma-ray glow from a region of intense star formation can perfectly mimic the expected signal from dark matter annihilation. This is the astronomical equivalent of trying to hear a single, specific instrument in a roaring symphony orchestra. Isolating the dark matter melody requires not just more data, but a deeper understanding of every other instrument in the cosmic ensemble. This is where instruments like the Fermi Large Area Telescope, or Fermi-LAT, come into play. This space-based gamma-ray observatory has been meticulously mapping the entire sky for over a decade, creating an incredibly detailed catalog of high-energy light sources. In the search for dark matter, Fermi-LAT isn't just looking for bright spots, it's searching for specific patterns within the gamma-ray fog. One key strategy is to look at places where dark matter is predicted to be especially dense. Dwarf spheroidal galaxies, for instance, are small, faint satellite galaxies orbiting our Milky Way. They are believed to be massively dominated by dark matter, containing very little of the ordinary gas and stars that would create confusing astrophysical gamma-ray backgrounds. They are considered pristine laboratories. If dark matter annihilates, these dwarfs should shine with a faint, characteristic gamma-ray glow. Fermi-LAT has scrutinized dozens of these dwarfs, and while it has placed incredibly stringent limits on what dark matter can and cannot do, a clear, unambiguous signal has thus far remained elusive. Another promising hunting ground is the very center of our own galaxy. Based on gravitational observations, the galactic center is thought to harbor an immense density of dark matter, which should make it a bright beacon of annihilation radiation. Indeed, Fermi-LAT and other telescopes have detected an intriguing excess of gamma rays emanating from this region. For a time, this galactic center excess generated tremendous excitement, as its properties seemed to align beautifully with predictions for certain dark matter particle models. However, the same region is also home to a zoo of complex astrophysical phenomena. A dense cluster of spinning pulsars, intense star-forming regions, and the supermassive black hole Sagittarius A star. Untangling a potential dark matter signal from this chaotic astrophysical foreground has proven to be exceptionally difficult, and the consensus is increasingly leaning toward a more conventional explanation, like a previously undetected population of thousands of millisecond pulsars. The frustration is palpable, but it is also a driving force for innovation. The inability to easily find a signal is forcing physicists to become more creative. They are developing increasingly sophisticated statistical methods to analyze the data, searching for more subtle signatures beyond a simple energy excess. Could there be a specific line in the gamma-ray spectrum, a sharp spike at an energy corresponding to the mass of a dark matter particle. Such a line would be far harder for conventional astrophysics to explain and would be a virtual smoking gun. Others are looking for correlated signals across different messengers. If a certain pattern of cosmic ray positrons is detected by MS and a specific pattern of gamma rays is seen by Fermi LT from the same region of sky, the combined evidence would be far more compelling than either alone. We are moving from an era of simple detection to one of multi-messenger astronomy, where cosmic rays, gamma rays, and even neutrinos are used together to solve the puzzle. The enigmatic connection between cosmic rays and dark matter represents a profound convergence of the largest and smallest scales in the universe. It ties the mysterious particles raining down on us to the invisible scaffolding that shapes the cosmos itself. Every high-energy positron or antiproton we detect is a potential clue, a fragment of evidence in the greatest detective story in science. While the definitive proof has not yet been found, the very act of searching is refining our theories and pushing our technologies to their limits. The absence of a clear signal is in its own way a form of data, telling us what dark matter is not and guiding us toward what it might be. This search forces us to look deeper into space and to think more creatively about the fundamental nature of reality, reminding us that the most profound answers often come from asking the most difficult questions. While we often picture cosmic rays as messengers from distant, violent events in the cosmos, their journey doesn't necessarily end with a flash of light in our upper atmosphere. Some scientists propose that their influence extends far beyond the detector, potentially touching something much more intimate and vital to life on Earth, our planet's climate. This leads us to one of the most fascinating and hotly debated hypotheses in modern science, the idea that cosmic rays might play a direct role in shaping Earth's weather by seeding cloud formation. The proposed mechanism is an intricate dance of particles and droplets. When a high-energy cosmic ray, typically a proton, smashes into a molecule in the upper atmosphere, it can create a cascade of secondary particles. Among these are free electrons and positive ions, atoms or molecules that have lost or gained an electric charge. These ions, the theory suggests, can act as magnets for water vapor and trace gases like sulfuric acid. In the complex chemistry of the atmosphere, these charged particles can significantly lower the energy barrier required for tiny aerosols to form and grow. Once these aerosols reach a certain size, they can serve as condensation nuclei, the essential seeds upon which water vapor condenses to form cloud droplets. More cosmic rays would therefore lead to more ions, which could lead to more potential seeds for clouds. Since clouds play a crucial role in regulating Earth's temperature by reflecting sunlight back into space and trapping heat, even a small change in global cloud cover could have a major impact on the climate. To test this idea under controlled laboratory conditions, scientists turned to the world's premier particle physics laboratory, CERN in Geneva. The Cosmics Leaving Outdoor Droplets or Cloud experiment was specifically designed to recreate the atmosphere inside a pristine stainless steel chamber. Using a beam of particles from CERN proton synchrotron to simulate cosmic rays, the international team of researchers can meticulously study how these artificial cosmic rays influence aerosol formation. The results from over a decade of experiments are both groundbreaking and nuanced. The cloud collaboration has confirmed that the ionizing radiation from cosmic rays does indeed enhance the rate of aerosol formation for certain atmospheric compounds, particularly those involving sulfuric acid and ammonia. It provides a clear physical mechanism, showing that the hypothesis is scientifically plausible and occurs in a controlled environment. However, translating this laboratory proof into a significant driver of global climate is where the intense controversy begins. The central claim of the hypothesis is that variations in the Sun's magnetic activity, which modulates the number of cosmic rays reaching Earth, could be a major cause of climate change. When the sun is more active, its strengthened magnetic field and solar wind better shield Earth from cosmic rays, leading to less ionization, fewer cloud seeds, and a warmer planet. When solar activity is low, more cosmic rays get through, potentially seeding more clouds and cooling the planet. Proponents of this idea point to intriguing historical correlations, such as periods like the Maunder Minimum in the 17th century, when both sunspots and cosmic ray flux were exceptionally high while Europe experienced a pronounced cold spell known as the Little Ice Age. Yet, the vast majority of climate scientists remain deeply skeptical, arguing that the evidence for a strong climatic effect is weak at best. Critics point out that while the laboratory mechanism is valid, its effect in the real-world atmosphere appears to be overshadowed by other, far more powerful factors. The production of cloud condensation nuclei from human activities, like industrial pollution and agricultural emissions, is orders of magnitude greater than any potential contribution from cosmic ray-induced ions. Furthermore, extensive studies looking for a clear statistical link between satellite-observed cloud cover and measured cosmic ray flux over recent decades have failed to find a robust global correlation. The planet has warmed dramatically over the last 50 years, a period which has seen no long-term trend in cosmic ray flux, effectively decoupling the two phenomena and pointing squarely to greenhouse gases as the dominant driver of modern climate change. This intersection of astrophysics and meteorology remains a captivating frontier. It shows how a particle born in the death throes of a star millions of light years away could, in theory, influence the tiny droplets in a cloud floating overhead. While the cosmic ray climate link is unlikely to be the primary engine of global warming, it serves as a powerful reminder of the profound and often unexpected interconnectedness of our universe. The research continues not to find an alternative to the established science of climate change, but to better understand the delicate and complex orchestra of forces that create the environment we call home. But the cosmic ray story doesn't end with the particles that first strike our atmosphere. Their collision sets off a spectacular chain reaction, creating a whole new shower of secondary particles that rain down upon the Earth. And among these, one type of particle stands out for both its utility and its mystery, the muon. Often described as a heavy, unstable cousin of the electron, the muon is a fundamental particle that should not, by all rights, exist for very long. With a lifetime of just over 2 microseconds, it would normally decay into other particles after traveling less than a kilometer. Yet we detect them constantly at the Earth's surface. This is a classic example of Einstein's theory of relativity at work because these muons are created traveling at nearly the speed of light. Time dilation stretches their fleeting existence from our perspective, allowing them to complete their journey from the upper atmosphere to our detectors. For decades, physicists have used these hardy particles as a natural probe, much like doctors use X-rays to peer inside ancient pyramids and map the interior of volcanoes. But more recently, these same muons have begun to reveal a deep and troubling inconsistency that points to a gap in our understanding of the universe's fundamental laws. This inconsistency is known as the muon puzzle, and it revolves around a simple, maddening question: where are all the extra muons coming from? When a high-energy cosmic ray proton collides with a nucleus in the upper atmosphere, it triggers a complex cascade known as an extensive air shower. Our best theoretical models, which incorporate the well-tested rules of the Standard Model of particle physics, allow us to predict how many secondary particles of each type, protons, neutrons, pions, kaons, and eventually muons, should be produced in this shower. For years, these models seemed reliable, but as our detectors grew more sophisticated, a persistent anomaly emerged. Experiments worldwide, from the Pierre Auger Observatory to the telescope array and beyond, began reporting the same thing. Their detectors were consistently counting significantly more muons than the models predicted. The discrepancy isn't small, we're talking about an excess of 30 to 60% more muons than our most advanced physics simulations say there should be. It's as if you carefully calculated the exact ingredients for a cake, followed the recipe precisely, and yet pulled from the oven a cake that was mysteriously, substantially larger. The implications of this muon surplus are profound because it strikes at the heart of our understanding of high-energy particle interactions. The process that creates these muons is a multi-step dance. The initial collision produces a variety of short-lived particles, particularly pions and kaons. These then decay, often producing muons and neutrinos. The key to the puzzle lies in the competition between two processes: how often these pions and kaons collide with other nuclei in the air versus how often they simply decay. If they collide, they produce more particles, feeding the shower. If they decay, they produce muons. Our models make very specific predictions about the probabilities of these events, probabilities that have been tested and verified in human-made particle accelerators. But the energies involved in a cosmic ray air shower are far beyond what we can create in even the Large Hadron Collider. The muon puzzle strongly suggests that when we push matter to these extreme energies, the rules of engagement change in ways we haven't yet accounted for. The models for these ultra-high-energy collisions, known as hadronic interaction models, appear to be missing a key piece of physics. Solving this puzzle is not just an academic exercise. It has real consequences for how we interpret every single cosmic ray detection. Muons are the workhorses of ground-based cosmic ray observatories. They are the particles that actually trigger the vast majority of the water tanks, scintillators, and other detectors that make up these massive arrays. The total number of muons a shower produces is directly used to estimate the energy and mass of the original primary cosmic ray that started the whole cascade. If our models are systematically underestimating the number of muons, then we might be misjudging the very nature of the particles we're trying to study. We could be incorrectly identifying a heavy nucleus like iron as a lighter proton simply because we're counting more muons than we think we should for a proton shower. This means the muon puzzle doesn't just call into question our particle physics. It potentially adds a layer of uncertainty to the entire cosmic ray mass spectrum, affecting our search for their origins and our understanding of their acceleration mechanisms. The quest to resolve this anomaly is driving innovation on two fronts. First, physicists are working to refine the hadronic interaction models, incorporating new data from the highest energy collisions at the LHC and exploring whether exotic, unknown states of matter could be produced in these atmospheric collisions, leading to enhanced muon production. Second, new generations of cosmic ray experiments are being designed with precise muon counting as a primary goal. The muon, a particle we thought we understood, has become a beacon pointing toward a frontier of physics we have yet to explore. It reminds us that even the most well-tested theories must constantly be questioned against the evidence provided by the universe's own, unimaginably powerful particle accelerators. While we often think of cosmic rays originating from isolated, cataclysmic events like supernova, some of the universe's most energetic particles may be born from a far more spectacular and rare kind of collision, the violent merger of two neutron stars. These events are not merely explosions, they are cosmic forges capable of creating the heaviest elements in the universe and potentially launching particles to energies that rival the most extreme cosmic rays we detect. To understand this incredible process, we need to rewind to one of the most significant astronomical events of the 21st century, the detection of gravitational waves from a neutron star merger known as GW170817. On August 17, 2017, the LIGO and Virgo gravitational wave observatories detected the distinctive ripples in spacetime caused by the final death spiral of two neutron stars. For the first time ever, this gravitational wave signal was accompanied by a flash of light across the electromagnetic spectrum. Telescopes around the world and in space swiveled to observe the event, witnessing a short gamma ray burst followed by a kilonova, a brilliant, rapidly fading glow caused by the radioactive decay of heavy elements like gold and platinum forged in the merger's aftermath. This single event, GW170817, ushered in the era of multimessenger astronomy, where we can study cosmic phenomena through gravitational waves, light, and particles simultaneously. But the story doesn't end with the light we see. It hints at the invisible particles that might also be produced. The sheer violence of a neutron star merger provides the perfect conditions for particle acceleration. As the two ultra-dense stellar corpses collide and coalesce, they can form a newborn black hole or a hypermassive neutron star surrounded by a torus of incredibly hot, magnetized debris. In a fraction of a second, this system can launch tightly focused jets of plasma at velocities excruciatingly close to the speed of light. It is within these relativistic jets that the acceleration of cosmic rays is thought to occur. The mechanism is a version of the same diffusive shock acceleration we see in supernova remnants, but dialed up to an almost unimaginable extreme. Particles, likely protons or heavier atomic nuclei, can become trapped between magnetic fields within the jet or at its leading edge. Each time they cross a shock front, they gain a massive boost in energy. In the chaotic, hyper-energetic environment of a jet from a neutron star merger, this process can potentially accelerate particles to energies that meet or even exceed the fabled GZK cutoff, creating the ultra-high-energy cosmic rays that have so confounded scientists. The connection to gamma-ray bursts is a critical piece of evidence. The short gamma-ray burst that accompanied GW170817 is believed to have been produced when the jet from the merger was pointed almost directly at Earth. This tells us that these mergers are indeed capable of producing the kind of focused, ultra-relativistic outflows required to accelerate particles to cosmic ray energies. Furthermore, the heavy elements synthesized in the kilonova ejector could provide the raw material, the atomic nuclei that get swept up and accelerated by these jets. This means a cosmic ray from a neutron star merger might not just be a proton. It could be a nucleus of gold, platinum, or another heavy element, literally a piece of stellar shrapnel from the creation of the universe's most precious metals. The hunt for definitive proof involves searching for other messengers from these events, particularly high-energy neutrinos. Neutrinos are the perfect because they travel in straight lines, unaffected by magnetic fields, and are produced alongside cosmic rays when accelerated protons collide with other particles. If a neutron star merger is indeed a potent cosmic ray factory, then a neutrino observatory like IceCube should detect a burst of these ghostly particles arriving from the same direction at the same time as the gravitational waves and the gamma-ray burst. While no such neutrino signal was conclusively identified from GW170817, future detections of closer mergers hold that promise. Finding that correlation would be the smoking gun, directly linking the merger to the acceleration of hadrons. This is why neutron star mergers are now considered one of the most promising candidates for solving the mystery of ultra-high-energy cosmic rays. They are engines of unbelievable power, operating in environments with gravity so strong and magnetic fields so intense that they can achieve what our galaxy's supernova cannot. They also occur frequently enough throughout the universe to potentially account for the number of extreme events we detect. Each time we observe one, through gravitational waves or light, we are potentially witnessing the activation of a natural particle accelerator of unparalleled ferocity. The cosmic rays that may originate from these events carry with them not only immense energy but also the very history of their creation, a story of collision, creation, and the violent birth of elements in the darkness of space. They represent a direct link between the gravitational wave sky and the particle detections on Earth, weaving together the stories of space-time, light, and matter into a single multi-messenger narrative. But while we have been looking to the most violent collisions and distant voids for answers, One of the most promising suspects in the case of the missing cosmic ray sources has been hiding in plain sight, relatively speaking, just 12 million light-years away. This is the peculiar and magnificent active galaxy known as Centaurus A. Unlike the blank voids that left us baffled, Centaurus A is a cosmic powerhouse we can actually see, and it presents a compelling package of evidence that makes it a prime candidate for being a significant contributor to the cosmic rays that wash over our Milky Way. What makes Centaurus A such a compelling suspect is its unique combination of proximity and activity. At a distance of about 12 million light-years, it is one of the closest active galaxies to our own, close enough for us to study its structure in remarkable detail. And it is anything but ordinary. Through a telescope, it reveals itself as a monstrous hybrid, the result of a past galactic collision. It has the classic dust lane of a giant elliptical galaxy, but this dark band is bisected by gigantic jets of plasma erupting from its core. This chaos is driven by a supermassive black hole at its heart, weighing in at about 55 million times the mass of our Sun, which is actively feeding on surrounding material. As matter spirals into this gravitational abyss, it doesn't go quietly. It unleashes tremendous energy and channels some of it into those colossal jets that blast outward for over 1 million light-years, far beyond the galaxy's visible boundaries. It is within these relativistic jets that physicists believe the acceleration of cosmic rays occurs. The same process of Fermi acceleration that works in supernova remnants is thought to operate here, but on a truly gargantuan scale. Charged particles can become trapped in the magnetic fields that are naturally generated and amplified within the jet. Each time they cross a shock wave or a turbulent region in this flow, they receive a massive kick of energy. The scale and power of Centaurus A's jets mean this process can, in theory, accelerate protons and atomic nuclei to the ultra-high energy levels that have so confounded us. We have a front row seat to a natural particle accelerator of epic proportions, and we've even seen the evidence of its work. The Fermi Gamma Ray Space Telescope has detected very high-energy gamma rays emanating from the giant lobes at the ends of Centaurus A's jets. This gamma ray emission is a crucial clue, as it is the telltale signature expected when accelerated cosmic rays, specifically protons, collide with other matter, producing pions that then decay into photons. It's the cosmic equivalent of finding gunpowder residue on a suspect's hands. Its relative proximity offers another huge advantage. It helps to sidestep the daunting problem of the GZK cutoff. Remember, the most energetic protons should lose energy over long distances due to interactions with the cosmic microwave background. But 12 million light-years is, in cosmic terms, just next door. A proton accelerated by Centaurus A could, in theory, make the journey to our galaxy without being completely drained of its ultra-high energy by the GZK process. This makes Centaurus a very plausible source for at least some of the extreme events recorded by observatories like the Pierre Auger Observatory, which has noted a statistical correlation between the arrival directions of the highest energy cosmic rays and the general location of this active galaxy. However, confirming this link with absolute certainty remains a formidable challenge, and the primary culprit is the same one that scrambles all cosmic ray paths: magnetic fields. While Centaurus A is close, the space between our galaxies is not empty. It is filled with the weak but pervasive magnetic fields of the intergalactic medium and our own local group of galaxies. A proton, being electrically charged, does not travel in a straight line. Its path is constantly bent and deflected by these magnetic fields. The amount of deflection depends on the particle's energy and the strength of the fields it encounters, both of which are poorly known. By the time a cosmic ray from Centaurus arrives at Earth, its arrival direction could be dozens of degrees away from its true point of origin. It's the ultimate cosmic curveball. This is why we can't simply point to a cosmic ray and then point a telescope back in a straight line to find Centaurus A. The path has been scrambled. The correlation is statistical, built up over thousands of detected events, showing a slight but significant excess arriving from that general region of the sky. This is why Centaurus is so much more than just a single candidate. It represents an entire class of sources. It is the closest and brightest example of a radio galaxy, a type of active galactic nucleus characterized by these powerful, large-scale jets. If Centaurus is indeed accelerating cosmic rays, then there are countless other similar galaxies throughout the universe, all potentially contributing to a diffuse background of high-energy particles. They could be the workhorses steadily feeding cosmic rays into the intergalactic medium, where they mix and diffuse before occasionally finding their way to our detectors. Centaurus provides a nearby laboratory to test this idea, to study the detailed physics of jet-driven acceleration in a system we can actually resolve. Every cosmic ray that might be traced back to its direction is a piece of evidence, not just for one galaxy, but for a fundamental mechanism of the universe, one that transforms the gravitational energy of supermassive black holes into a rain of particles that echoes across millions of light-years of space. Just as we look to the cosmos for the grandest sources of cosmic rays, their influence can also be measured in the subtle, unexpected behaviors of our own robotic explorers sent out into the solar system. This brings us to a captivating mystery that puzzled NASA engineers for decades, a story that begins with two iconic spacecraft and an anomaly so persistent it briefly tempted theorists to rewrite the laws of gravity itself. This is the tale of the Pioneer anomaly, a classic case of a cosmic detective story where the prime suspect for a time was the subtle, relentless pressure of cosmic rays. The Pioneer 10 and 11 probes, launched in the early 1970s, were true trailblazers, the first human-built objects to travel through the asteroid belt and return stunning close-up images of Jupiter and Saturn. Long after completing their primary missions, they continued to stream data back to Earth as they hurtled toward the outer reaches of our solar system. But by the 1980s, deep space navigators noticed something peculiar. Both spacecraft were experiencing a tiny, unexplained, and constant acceleration back toward the Sun. This minuscule push, smaller than a billionth of the gravity we feel on Earth, was nonetheless a significant deviation from their predicted trajectories. It was as if a faint, invisible hand was ever so gently applying the brakes to their journey into interstellar space. For years, this anomaly defied explanation, and among the many exotic theories proposed, one involved cosmic rays. The idea was that the particles decay products within the spacecraft's nuclear power sources, or the pressure of the cosmic rays themselves striking the craft, could be generating a small but measurable force. It was a testament to the pervasive nature of these particles that they were considered a plausible culprit for such a delicate physical effect. Ultimately, after a monumental effort of data archaeology and sophisticated modeling, a far more mundane explanation was found. The anomalous thrust was traced to a simple thermal effect, the faint, uneven radiation of heat from the spacecraft's radioactive power generators. As these units decayed, they emitted heat photons. Because of the probe's unique geometry, with their large dish antennas blocking the rear, slightly more heat was radiated from the forward-facing side. This created a tiny photon rocket effect, gently pushing the spacecraft backward. The case was closed, but the legacy of the Pioneer anomaly is profound. It demonstrates with exquisite precision how even the most subtle physical phenomena must be accounted for in the extreme environment of space, and it opened the door to a much broader appreciation of how cosmic rays truly do interact with our technology. While they weren't the cause of the Pioneer anomaly, cosmic rays present a far more direct and insidious threat to spacecraft and satellites. These particles are not just passive travelers, they are a form of ionizing radiation, and their impact on sensitive electronics is a constant concern for engineers. The most common and disruptive effects are single event effects, or SEE, when a single high-energy cosmic ray particle, or one of the secondary particles it creates in a collision, strikes a microscopic transistor on a computer chip, it can deposit a concentrated burst of charge. This can have several dramatic consequences. A single event upset can cause a bit in a memory cell to flip from a 0 to a 1 or vice versa, corrupting data and potentially issuing an erroneous command to a spacecraft. More severely, a single event latch-up can create a short circuit within the chip, leading to a surge of current that can literally burn out the component if power isn't immediately cut. There are even single-event burnouts and gate ruptures that can permanently destroy power transistors. The history of space exploration is littered with examples of these cosmic ray-induced glitches. Satellites have gone into safe mode, scientific instruments have reset themselves, and communication links have been temporarily lost, all traced back to a single subatomic particle from the depths of the galaxy striking at exactly the wrong place at the wrong time. For missions operating in the harsher radiation environment beyond Earth's protective magnetic field, such as the Juno probe at Jupiter or the upcoming Europa Clipper mission, the challenge is even greater. These effects are not merely inconvenient, they directly influence the design, cost, and longevity of every single piece of hardware we send into space. This relentless bombardment has forced the aerospace industry to develop an entire arsenal of mitigation strategies. Engineers employ radiation-hardened microprocessors and memory chips, which are physically designed to be more resistant to these disruptive charge bursts. They add shielding around critical components, using materials like aluminum or tantalum to absorb the energy of incoming particles. They design sophisticated fault detection and correction systems into their software, allowing a spacecraft to recognize when its memory has been corrupted and automatically correct the error or reboot a system. For particularly sensitive missions like those carrying astronauts, monitoring the real-time flux of cosmic rays becomes a critical part of operational planning, potentially leading to delays in activities like spacewalks during periods of high solar activity, which can amplify radiation levels. The silent, invisible rain of cosmic rays has shaped the very architecture of our spacefaring technology, a constant reminder that venturing beyond our atmospheric cocoon means contending with the fundamental forces of the universe. While protons and heavier nuclei may dominate the cosmic ray population, their lighter, nimble cousins, electrons, tell a story that is equally fascinating but entirely their own. To understand the cosmic ray electron spectrum is to study the universe's most fleeting and energetic messengers, particles whose journeys are marked by rapid energy loss and whose origins are consequently locked within our local galactic neighborhood. Unlike a proton, which can hold onto its energy for millions of years as it bounces through the Milky Way's magnetic maze, an electron is a fickle traveler. Its tiny mass makes it incredibly susceptible to energy loss, primarily through two processes: synchrotron radiation, where it bleeds energy by spiraling around magnetic field lines, and inverse Compton scattering, where it loses energy by colliding with and boosting the energy of lower energy photons. This means the highest energy electrons we detect cannot have traveled more than a few thousand light-years. They are a snapshot of recent and nearby cosmic activity, offering a uniquely local perspective on the galaxy's particle accelerators. When we plot the number of these electrons against their energy, the resulting spectrum is not a smooth, featureless curve. Experiments like the Fermi Large Area Telescope and the HESS array of ground-based telescopes have revealed a spectrum rich with intriguing details, most notably a significant excess of electrons at very high energies, beginning around 1 tera-electronvolt and extending dramatically beyond. This is not what standard models predicted. If the primary source of cosmic ray electrons were distant supernova remnants, their numbers should show a steady, unbroken decline at these energies due to the severe radiative losses. The clear and persistent excess tells us that something else, something potent and relatively close by, must be continuously injecting a fresh supply of these high-energy particles into the local interstellar medium. Identifying this mysterious local source has become a major focus of modern astrophysics, with the investigation centering on two primary classes of suspects. The first is a collection of nearby pulsars. These spinning neutron stars, like the famous Geminga or the Vela pulsar, are known to generate powerful winds of relativistic particles. As electrons are accelerated in the intense magnetic fields around these objects, they can radiate away their energy, producing the bright nebulae we see around them. It is entirely plausible that a population of such nearby pulsars could be responsible for the observed electron excess, their combined output creating the elevated flux we measure. The challenge lies in precisely modeling the propagation of these electrons from each candidate pulsar to Earth, accounting for the complex magnetic fields and radiation fields they must traverse to see if the predicted spectrum matches the exquisite data from Fermi and ESS. The second, and far more exotic, suspect is the annihilation or decay of dark matter. Certain theoretical models of weakly interacting massive particles predict that when two of these particles collide, they could annihilate into a shower of standard model particles, including electron-positron pairs. The energy spectrum of these resulting electrons would have a very specific shape, often characterized by a sharp cutoff at an energy corresponding to the mass of the dark matter particle. The observed high-energy excess shows a noticeable steepening or cutoff around 2 teraelectronvolts, a feature that some researchers argue could be the long-sought fingerprint of a dark matter particle with a mass of around 1.5 teraelectronvolts. This tantalizing possibility has fueled intense debate, though distinguishing a dark matter signature from the collective rumble of numerous pulsars remains an enormous analytical challenge. Ultimately, the very property that makes cosmic ray electrons so difficult to study, their rapid energy loss, is also what makes them such powerful astronomical tools. Because they cannot travel far, a detected high-energy electron is a guaranteed signpost to a recent and local cosmic event. Their spectrum acts as a direct probe of the accelerator itself and the environment through which they traveled. By meticulously measuring the subtle features and cutoffs in this spectrum, scientists are not just looking for a source, they are conducting an archaeological dig into the recent history of our galactic vicinity, uncovering the locations and properties of the most energetic engines operating near our solar system. Each high-energy electron is a fragile, high-speed communique, and its successful delivery to our detectors provides a rare and valuable glimpse into the ongoing particle acceleration happening right in our own celestial backyard. But if our local galactic neighborhood and nearby active galaxies provide one piece of the puzzle, then we must now turn our gaze to the very heart of our own Milky Way, to a region of such immense density and violence that it has long been suspected as a prime engine for the cosmic rays permeating our galaxy. This is the galactic center, a place where the normal rules of astronomy are pushed to their absolute limits. At a distance of 26,000 light-years, it is a chaotic and crowded environment, home to millions of stars packed into a relatively small volume, vast clouds of turbulent gas, and the ultimate enigma at its core, the supermassive black hole known as Sagittarius A star. This entire region is a pressure cooker of astrophysical activity, making it a prime candidate for a prolific cosmic ray factory. The sheer concentration of potential accelerators here is staggering. Unlike the quiet suburbs of the galaxy where our solar system resides, the galactic center is a non-stop festival of extreme events. It contains some of the most massive star clusters known, where young, brilliant stars live fast and die young in spectacular supernova explosions. The collective winds from these stars and the expanding shells of their remnants create a complex web of colliding shock waves. any one of which could serve as a potent site for particle acceleration through the well-established process of diffusive shock acceleration. But towering above all these phenomena is the 4 million solar mass giant at the center, Sagittarius, a star. While it is relatively quiet now, evidence suggests it has not always been so. Geological records on Earth and observations of nearby clouds like the Fermi bubbles suggest that several million years ago, Sagittarius, a star, underwent a period of tremendous activity, likely consuming a large amount of matter and unleashing an outburst of energy that would have dwarfed anything we see today. Such an outburst would have created shocks and jets capable of accelerating particles to energies that could still be echoing through the galaxy today in the form of cosmic rays. The hunt for evidence of this acceleration hinges on our ability to detect the secondary signatures these particles leave behind. We cannot see the cosmic rays directly from such a distance, but we can observe the brilliant gamma-ray light they produce. When accelerated protons collide with the dense clouds of gas that populate the galactic center, they produce neutral pions that immediately decay into high-energy gamma rays. Telescopes like the High-Energy Stereoscopic System, or HESS, and the Fermi Gamma Ray Space Telescope have done exactly that, mapping an intense and extended glow of very high-energy gamma rays emanating from the central 100 light-years of our galaxy. This emission isn't just a point source centered on the black hole. It is correlated with the massive molecular clouds that surround it. This is a crucial clue. It suggests that these clouds are not the source themselves, but are instead being illuminated by a sea of cosmic rays that is bathing the entire region. The cosmic rays are being produced by one or more powerful accelerators nearby, and then slamming into the dense gas, revealing their presence through this telltale gamma-ray glow. However, interpreting this data is an exercise in extreme astrophysical detective work, fraught with challenges and competing theories. The primary difficulty is the overwhelming background noise. The galactic center is the brightest source of almost everything in the sky: radio waves, infrared radiation, X-rays, and gamma rays. Teasing apart the specific gamma-ray signal caused by proton collisions from other processes like electron radiation is incredibly complex. Furthermore, the extreme density of material means that the cosmic rays we detect from Earth might not have traveled far from their source. They could be produced locally within the region and then quickly absorbed by the same gas clouds, making it difficult to determine if they eventually escape to enrich the wider galaxy. The other major puzzle is pinpointing the exact accelerator responsible. Is the gamma-ray glow the result of a single past cataclysm, like a giant outburst from Sagittarius, a star, whose accelerated particles are still interacting with the clouds today? Or is it the collective product of many recent supernovae and the fierce stellar winds from the massive stars in the central cluster? The data currently suggests a hybrid model where a population of transient accelerators, together with a possible past outburst from the central black hole, creates a persistent and powerful reservoir of high-energy particles. Studying this region is like trying to listen to a single instrument in the middle of a symphony orchestra performing at full volume, yet the potential reward is immense. If the galactic center is indeed a major source of galactic cosmic rays, it would mean that the most energetic particles striking our atmosphere began their journey in the most dynamic and violent place in the Milky Way. They would carry with them the imprint of processes we can only otherwise observe from a great distance. Each detection of a cosmic ray that might be traced back to this general direction is a tangible piece of the galactic center's furious activity, a messenger from a realm of extreme gravity and stellar density that is otherwise hidden from view by vast clouds of cosmic dust. It reinforces the idea that our galaxy is not a static collection of stars, but a dynamic ecosystem with its heart serving as a powerful engine, continually pumping energy and particles into the galactic halo, influencing the very cycle of star formation and the evolution of the Milky Way itself. But the composition of cosmic rays is more than just a catalog of elements. It is a complex forensic record that can be used to reconstruct the entire life story of these particles, from their acceleration to their long journey across the galaxy. This brings us to a particularly elegant cosmic detective story, one involving three of the lightest elements in the universe. It's known as the lithium-beryllium-boron problem, and it provides a brilliant example of how an apparent anomaly in our data can unlock a much deeper understanding of cosmic reality. If you were to take a sample of the cosmic material that makes up the solar system or the primordial gas between the stars, you would find that lithium, beryllium, and boron are incredibly rare. They are thousands of times less abundant than common elements like carbon or oxygen. This makes perfect sense from the perspective of cosmology. These light elements are not forged in the great furnaces of stars or in the Big Bang itself in any significant quantity. They are fragile and are actually destroyed in those high-temperature environments. So, imagine the surprise of early cosmic ray researchers when they discovered that these same three elements are extraordinarily abundant in the cosmic ray flux. In fact, the ratios of lithium, beryllium, and boron to carbon and oxygen are hundreds of thousands of times greater in cosmic rays than they are in the average composition of our solar system. This was not just a small discrepancy, it was a monumental contradiction that demanded an explanation. The resolution to this puzzle is not that these elements are being created in some unknown source, but rather that they are being manufactured during the journey itself. They are what physicists call secondary cosmic rays. The process is known as spallation, and it is a form of cosmic erosion. It works like this. Imagine a primary cosmic ray, such as a nucleus of carbon or oxygen, that has been accelerated to near light speed by a supernova remnant. As this high-energy nucleus travels through the Milky Way, it doesn't have a clear path. It must navigate the thin fog of atoms that makes up the interstellar medium, mostly hydrogen and helium. Every so often, this high-speed carbon or oxygen nucleus will collide head-on with a nucleus of this interstellar gas. The impact is tremendously violent. It's less like a collision and more like a fragmentation grenade going off. The energetic collision shatters both nuclei into pieces. The heavier incoming nucleus, like carbon, can be broken apart, and among those fragments are the lighter nuclei of lithium, beryllium, and boron. In this way, the interstellar medium itself acts as a gigantic target, and the primary cosmic rays are the projectiles that create these secondary elements through high-energy collisions. This realization transforms the lithium-beryllium-boron problem from a confusing anomaly into one of the most powerful diagnostic tools in all of astrophysics. The abundance of these secondary nuclei becomes a direct measure of how much material a cosmic ray has traveled through before it reaches our detectors. Think of it like this: if you were walking through a light mist, you wouldn't get very wet, but if you had to walk through a dense fog for a long time, you would become soaked. In the same way, the amount of lithium, beryllium, and boron we detect tells us how soaked the cosmic rays are with the evidence of their journey through the interstellar fog. By precisely measuring the ratios of these secondary elements to their primary parents, like boron to carbon or lithium to oxygen, scientists can calculate what is known as the path length or grammage. This is not a measure of distance in light years, but rather the total density of material the particles have encountered, measured in grams per square centimeter. It's the integral of the density of the interstellar medium over the entire winding path the particle took. The results of this cosmic accounting are fascinating. The calculated path length reveals that the average cosmic ray has traveled through a significant amount of material before reaching us, equivalent to a journey through about 3 grams of matter per square centimeter. To put that in perspective, if you could somehow stretch out all the atoms a cosmic ray has encountered and lay them in a flat sheet, that sheet would be about the thickness of a 1-pound book held up on its edge. This might not sound like much, but given that the interstellar medium is an incredibly thin vacuum, far better than any we can create on Earth, this amount of material implies a truly epic voyage. The particles must have zigzagged back and forth across the galaxy for millions of years, trapped by the Milky Way's magnetic fields before finally arriving at Earth. This also allows us to estimate their age. By combining the path length with models of the average density of the galaxy, we find that most cosmic rays have been traveling for somewhere between 10 and 20 million years before we detect them. They are not fresh from the source, they are ancient travelers, their composition forever altered by their long and turbulent voyage through the magnetic highways and byways of the Milky Way. The lithium-beryllium-boron problem, therefore, does much more than solve a compositional mystery. It opens a window into the entire life cycle of matter within our galaxy. These secondary elements are the indelible fingerprints left on a cosmic ray by its interaction with the interstellar medium, the silent witness to a journey of immense duration and complexity. By reading these fingerprints, we learn that our galaxy is not just a collection of stars and empty space, but a dynamic ecosystem where matter is constantly being recycled, accelerated, and transformed. The cosmic rays we collect are not pristine samples from their sources. They are weathered and evolved travelers, and their altered state tells the rich story of their long journey through the cosmic ocean. While we often explore cosmic rays as astrophysical messengers or technological nuisances, their influence extends to a realm far more intimate and profound, the very fabric of life itself. From the subtle dance of evolution on Earth to the stark dangers faced by astronauts, these high-energy particles engage in a constant, invisible interaction with biology, shaping destinies on a cellular level. The primary mechanism for this impact is ionizing radiation. When a cosmic ray, or more commonly one of the millions of secondary particles it creates in an air shower, streaks through living tissue, it can act like a microscopic bullet. It has enough energy to knock electrons loose from atoms, creating charged ions that can break the delicate chemical bonds within molecules. The most critical target is the intricate double helix of DNA. A direct hit can shatter strands, causing double-strand breaks that are difficult for a cell to repair correctly. Even a near miss can create a shower of free radicals, highly reactive molecules that then go on to wreak havoc, causing mutations, corrupting genetic information, and potentially triggering cell death or, in the worst case, the uncontrolled cell growth we know as cancer. This persistent, low-level background of genetic damage is not merely a destructive force. It is also a silent engine of mutation, a fundamental driver of evolution. The rate of genetic mutation provides the raw material upon which natural selection acts. If the environment changes, a population needs a diverse set of genetic traits to draw upon for survival. Cosmic rays, by contributing to that mutation rate, have likely played a role in introducing the genetic variations that have allowed life to adapt and evolve over billions of years. It is a humbling and awe-inspiring thought that the fate of a species, the rise and fall of evolutionary lines, could be partly influenced by events occurring in distant supernova or active galaxies millions of light-years away. The story of life on Earth is inextricably interwoven with the history of the cosmos, connected by these invisible, energetic threads. For the vast majority of Earth's inhabitants, however, this cosmic influence is heavily muted by two magnificent planetary shields, the atmosphere and the magnetosphere. Our planet's magnetic field acts as a first line of defense, deflecting a significant portion of the charged particles away from Earth and toward the poles where they create the beautiful auroras. The atmosphere, a dense blanket of gas miles thick, serves as a vast sacrificial barrier. The cascading air showers initiated by incoming cosmic rays expend most of their energy in the upper atmosphere, creating a protective ceiling that drastically reduces the radiation dose we receive at the surface. This natural shielding has been absolutely essential for the development of complex life, providing a relatively safe haven where DNA could replicate and organisms could thrive without being constantly bombarded by lethal levels of radiation from space. The strength of this shielding, however, is not constant. It fluctuates with the 11-year cycle of the Sun. During solar maximum, when our star is most active, its strengthened magnetic field and intensified solar wind puff out, helping to block incoming galactic cosmic rays from reaching the inner solar system. But during solar minimum, this protective heliosphere weakens. With the Sun's magnetic shield diminished, the flux of galactic cosmic rays penetrating Earth's environment increases significantly. This cyclical variation means that the biological impact of cosmic rays on Earth is not static. It pulses in time with the heartbeat of our star. Researchers continue to investigate whether these periods of increased cosmic ray flux have any detectable long-term effects on cloud formation, mutation rates, or even the climate, adding another layer of complexity to our understanding of Earth's place in the cosmic environment. For astronauts venturing beyond Earth's protective cocoon, the cosmic ray threat shifts from a theoretical evolutionary driver to an immediate and serious occupational hazard. In the void of space or on the surface of the Moon or Mars, there is no thick atmosphere to absorb incoming particles. Astronauts are exposed to a continuous, low-dose rain of high-energy radiation, primarily galactic cosmic rays and occasional intense bursts from solar particle events. This exposure poses significant risks, including a higher lifetime chance of developing cancer and potential damage to the central nervous system that could affect cognitive function on long-duration missions. The most insidious challenge is posed by heavy ion cosmic rays like iron nuclei. These densely ionizing particles can cause severe, localized clusters of cellular damage that are particularly difficult for the body to repair, leading to concerns about long-term health effects even after astronauts return home. This reality makes cosmic ray mitigation a central, unsolved problem for the future of human space exploration. A mission to Mars, which could take over 2 years, would expose crews to radiation levels that push far beyond current safety limits. Shielding on spacecraft is a tremendous engineering challenge because deflecting high-energy heavy ions requires massive amounts of material, making ships impractically heavy. Scientists are investigating innovative solutions, from developing lighter, more effective shielding materials like hydrogen-rich polymers to the futuristic concept of creating artificial magnetic fields around spacecraft that would mimic Earth's magnetosphere. Some are even looking at pharmacological countermeasures, drugs that would help the body better repair radiation-induced DNA damage. The success of these endeavors will determine not just the safety of astronauts, but the very feasibility of humanity becoming a multi-planetary species. Our ability to overcome this invisible barrier erected by the cosmos itself will ultimately define how far we can journey into the final frontier. Yet for all the powerful evidence pointing toward active galaxies like Centaurus A, the ultimate prize in cosmic ray astronomy is not a statistical correlation, but a single, definitive detection, a direct, unambiguous line drawn from an individual cosmic ray back to its source. This brings us to one of the most tantalizing clues in this decades-long search, the so-called Auger hotspot. Imagine a map of the entire sky, each point representing the arrival direction of an ultra-high-energy cosmic ray. For the most part, this map appears as a random, uniform sprinkle, a testament to how magnetic fields scramble their paths. But when the scientists at the Pierre Auger Observatory in Argentina focused only on the very highest energy events, those with energies above 58 exa-electronvolts, a pattern began to emerge from the chaos. They noticed a statistically significant clustering, an excess of arrivals from a broad region of the sky, roughly the size of 20 full moons, centered near the constellation Centaurus. This was not a random fluctuation. The chance of it happening randomly was calculated to be less than 1 in 17,000. They had found a hotspot. This discovery was monumental because it represents the strongest large-scale anisotropy ever detected for these enigmatic particles. It's a clear signal that, despite the magnetic scrambling, the very highest energy cosmic rays are not arriving from all directions equally. There is a discernible bias, a faint but persistent whisper pointing back toward a specific part of the universe. The immediate and obvious suspicion fell upon the most prominent object in that general direction, the active galaxy Centaurus A. Its proximity and violent nature make it a prime suspect, and the hotspot's location aligns beautifully with its position in the sky. It seemed for a moment that the mystery was solved. But the universe is rarely so straightforward. The Auger hotspot is not a precise pinprick of light centered exactly on Centaurus A. It is a broad, smeared-out region, and within its boundaries lie other potential culprits. The quest quickly expanded from confirming a single source to a full-scale astronomical investigation, with telescopes across the globe and in space scanning the hotspot region for any object capable of such immense power. The search zeroed in on two main classes of extreme galaxies. The first, as expected, is active galactic nuclei like Centaurus A, with their supermassive black hole engines and colossal jets. The second is starburst galaxies. These are not defined by a single central monster, but by a frenzy of collective stellar violence. In a starburst galaxy, stars are forming at a rate hundreds of times faster than in our own Milky Way. This epidemic of birth leads to an epidemic of death, with supernova explosions occurring frequently. The combined, overlapping shock fronts from all these simultaneous stellar cataclysms could create a widespread and potent accelerator, capable of producing the intense particle energies we observe. The hotspot region contains several of these stellar factories, adding more candidates to the list and complicating the detective work. The challenge of definitively linking the hotspot to a specific source perfectly illustrates the fundamental problem of charged particle astronomy. The broad, smeared nature of the hotspot is a direct result of magnetic deflection. A proton arriving from the direction of Centaurus A does not travel in a straight line. Its path is bent and twisted by the weak but pervasive magnetic fields that fill the space between galaxies. The amount of bending depends on the particle's energy and the unknown strength of these intergalactic fields. By the time the particle reaches us, its arrival direction could be many degrees away from its true origin. The hotspot we see is essentially a magnetic lensing effect, a blurred image of the true source region. This is why the anisotropy is statistical. It requires collecting many events to see the pattern of a blurred picture emerge from the noise. We are not seeing the source itself, but its shadow, distorted by the magnetic fields of the cosmos. Despite this blurring, the Auger hotspot remains one of the most important discoveries in the field. It provides the best evidence yet that ultra-high-energy cosmic rays are not born in the complete voids of intergalactic space, but are associated with the most energetically dense environments in the universe, the hearts of active galaxies and the cores of starburst galaxies. It tells us that the accelerators are out there and we are looking in the right places. Each new detection added to the Auger dataset sharpens this blurred image ever so slightly. Future observatories with even larger collection areas will detect more of these rare events, allowing us to move from a broad hotspot to a sharper one, and perhaps one day to a single, undeniable point on the sky. The hotspot is not the end of the journey, but the most promising signpost we have found, guiding us toward a future where we can finally point to a distant galaxy and say with certainty, there. That is where the universe's most powerful particle was launched. But even as we map the known accelerators and trace the statistical whispers from hotspots, our telescopes are revealing an even deeper layer of cosmic mystery. Across the galaxy, instruments like the high-energy stereoscopic system and Veritas are pinpointing brilliant sources of very high-energy gamma rays. Yet when astronomers swing other telescopes, those sensitive to radio waves, infrared light, or X-rays, to the very same coordinates, they often find nothing. No pulsar, no supernova remnant, no active galaxy, just an empty patch of sky glowing with invisible tera-electron-volt light. These are the unidentified TV sources, cosmic ghosts that astronomers have nicknamed dark accelerators, and they represent one of the most compelling frontiers in our search for the origins of cosmic rays. The existence of these dark accelerators is a profound puzzle because that brilliant gamma-ray light is itself a crucial clue. In many cases, this specific type of emission is a classic signature of powerful proton collisions. The process is like a cosmic billiards game. When a high-energy cosmic ray proton smashes into a slow-moving proton within a cloud of gas, the collision can produce a neutral pion, a subatomic particle that almost immediately decays into two high-energy gamma rays. Therefore, a bright, concentrated source of these gamma rays strongly implies the presence of a nearby cosmic ray accelerator, a natural particle collider pumping protons into a dense target like a cloud of molecular gas. We are effectively seeing the glowing crater formed by the impact of a proton beam. The frustrating and thrilling part is that we can see the glowing crater, but we cannot clearly identify the gun that fired the shot. This disconnect has led to a fascinating array of theories, each proposing a different type of hidden engine. One leading idea involves ancient, faded pulsars. A pulsar can generate powerful winds of particles long after its visible light has dimmed to near invisibility. This pulsar wind nebula could be accelerating particles to high energies, and if it's located near a dense molecular cloud, those particles would collide with the gas and produce the telltale gamma rays we see. The accelerator would be the pulsar, but it might be so old and faint at other wavelengths that it effectively becomes a dark gamma ray-only object. Another compelling theory suggests that we might be seeing the aftermath of a recent supernova explosion that occurred inside a particularly dense stellar nursery. The expanding shock wave would be an efficient particle accelerator, but the entire event could be hidden from our optical and X-ray telescopes by thick, obscuring dust clouds, only revealing its presence through the penetrating power of gamma rays. The most exciting possibility, however, is that these dark accelerators represent something entirely new, a class of astronomical object we haven't even thought of yet. Could they be the graves of massive stars that collapse directly into black holes with no visible supernova explosion? Or perhaps clusters of white dwarf stars engaging in some exotic form of particle acceleration? Each unidentified source is a blank space on our celestial map, a placeholder for a discovery waiting to happen. They are a stark and humbling reminder that our census of the universe's most energetic phenomena is still incomplete. We have built magnificent machines to see the invisible light of the cosmos, and in doing so, we have discovered that we still don't know what we're looking at. These dark accelerators are not just cosmic ray factories, they are direct challenges to our understanding, pushing us to look deeper, think more creatively, and ultimately expand our catalog of the universe's fantastic and varied engines. Yet, even amidst these grand puzzles of extragalactic origins and dark accelerators, there exists a far more subtle and rhythmic cosmic phenomenon, one that plays out with the reliable regularity of a celestial clock. This is the cosmic ray diurnal variation, a slight but measurable daily fluctuation in the intensity of cosmic rays reaching Earth. Unlike the cataclysmic events that produce the most energetic particles, this variation is not about the sources themselves, but about the intricate magnetic environment through which they must travel to reach us. It is a story woven from the daily interplay between Earth's rotation, the Sun's constant outflow, and the vast invisible architecture of the solar system's magnetic fields. The primary cause of this daily rhythm is our planet's own motion. As Earth spins on its axis once every 24 hours, our position within the flowing river of the solar wind continually changes. The solar wind is not a smooth, uniform breeze. It is a supersonic stream of charged particles and embedded magnetic field lines constantly flowing outward from the Sun. This creates a magnetic environment around Earth that is not perfectly symmetrical. Think of it as trying to walk through a strong, steady wind. The pressure you feel on your body changes depending on whether you're walking directly into the wind with it at your back or sideways to it. For a cosmic ray, which is itself a charged particle, this wind is the solar wind's magnetic field. The ease with which it can approach Earth depends on the angle at which it encounters this flowing magnetic medium. Here's how the daily cycle unfolds. Cosmic rays are positively charged particles, primarily protons. Their paths are deflected by magnetic fields according to a principle called the Lorentz force, which causes them to drift in specific directions. In the configuration of the interplanetary magnetic field, there is a predicted drift direction for these particles. During the local afternoon on Earth, around 2 to 4 p.m., our planet's rotation places a given point on the surface in what is known as the favored direction for this drift. At this time, the geometry of the global magnetic field makes it slightly easier for cosmic rays to penetrate inward. Conversely, during the early morning hours around 2 to 4 a.m., the same location is in an unfavored direction, making access more difficult. The result is a small but consistent daily wave in the data from cosmic ray detectors around the world, a gentle peak in the afternoon and a trough in the pre-dawn hours. This seemingly minor effect is far more than a curiosity. It is an incredibly powerful diagnostic tool. By meticulously measuring the precise timing, amplitude, and even the harmonics of this daily wave, scientists can indirectly probe the structure and behavior of the solar wind and the interplanetary magnetic field far from Earth. The exact shape of the diurnal variation is exquisitely sensitive to conditions in the heliosphere. For instance, the presence of high-speed solar wind streams flowing from coronal holes on the Sun can sharpen and shift the timing of the peak. Major disturbances like interplanetary shocks from coronal mass ejections can completely disrupt the pattern, wiping out the diurnal variation entirely for a short period before it re-establishes itself. By monitoring these subtle changes in the cosmic ray tide, researchers can infer the properties of the solar wind, its speed, density, and magnetic field polarity without having to send a probe to measure it directly at every point in space. This application is crucial for the practical and increasingly critical field of space weather forecasting. Our modern technological civilization is deeply vulnerable to the Sun's outbursts. A powerful coronal mass ejection aimed at Earth can induce massive electrical currents in power grids, causing widespread blackouts. It can damage satellites, disrupt GPS navigation, and pose a severe radiation hazard to astronauts and even high-altitude aircraft passengers. The diurnal variation of cosmic rays acts as an early warning system. A sudden damping or distortion of the daily pattern can be one of the first indicators that a shock wave from a solar storm has arrived in the inner solar system, giving precious extra hours to prepare and protect vital infrastructure. By understanding these subtle cosmic ray rhythms, we are learning to read the magnetic mood of our star, translating the silent, daily pulse of particles into a language that helps us safeguard our way of life. It is a profound reminder that even the most predictable patterns in nature can hold the key to anticipating its most violent and unpredictable outbursts. For centuries, astronomy was the science of light. We built telescopes to collect photons, from the gentle warmth of infrared to the piercing energy of gamma rays, and pieced together the universe from this single luminous messenger. But the cosmos speaks in more than one language. It converses through the silent, ghostly passage of neutrinos, the rippling of space-time in gravitational waves, and the relentless, charged particle rain of cosmic rays. To truly listen, we had to learn to understand them all at once. This is the heart of the Multimessenger approach, a revolutionary new era in astrophysics where we are no longer merely stargazers, but cosmic translators, synthesizing information from these wildly different signals to build a complete picture of the universe's most extreme events. It is a collaborative effort on a planetary scale, and it is our greatest hope for finally solving the enduring mystery of where cosmic rays are born. The immense power of this approach lies in the unique strengths and weaknesses of each messenger. Think of them as a team of expert witnesses, each with a different piece of the story. Photons, our traditional informant, give us a beautiful and detailed view of an event, but they can be scattered, absorbed, or obscured by cosmic dust. Cosmic rays carry direct physical information about their source, like its elemental composition, but their charged nature means magnetic fields bend their paths, erasing their origin point. Neutrinos, being nearly massless and neutral, fly in perfectly straight lines, unaffected by magnetic fields or matter, pinpointing their source with flawless accuracy. But they are infuriatingly difficult to detect, requiring enormous buried detectors like Ice Cube at the South Pole. Gravitational waves tell us about the dynamics of massive objects moving at relativistic speeds, like colliding black holes or neutron stars, providing a completely new sense that is blind to light but exquisitely tuned to the warping of spacetime itself. By combining these testimonies, we can achieve what is impossible with any one messenger alone. A single high-energy cosmic ray detection is a mystery. But if, at the same moment that cosmic ray hits Earth, a neutrino observatory like Ice Cube detects a neutrino from the same patch of sky, and a gamma-ray telescope sees a brilliant flash from that exact direction, the case is suddenly solved. The cosmic ray confirms that particles are being accelerated, the neutrino points directly back to the source, and the gamma-ray flash tells us about the explosive environment that launched them. This isn't theoretical, we have already seen its potential. In 2017, the LIGO and Virgo observatories detected gravitational waves from the merger of two neutron stars. Within seconds, telescopes across the globe and in space swiveled to observe the event, detecting a short gamma-ray burst and the glowing kilonova that forged heavy elements like gold. While a definitive neutrino signal wasn't recorded, the event was a stunning proof of concept. It showed the entire astronomical community moving in lockstep, and it provided a complete narrative of a cosmic cataclysm, from the initial inspiral of the stars to the creation of stellar shrapnel. For cosmic ray astrophysics, the most tantalizing multi-messenger partner is the neutrino. This is because neutrinos are a direct byproduct of the same process that creates cosmic ray protons. The connection is known as the pion production pathway. When a high-energy proton, a potential cosmic ray, collides with another proton or a photon near its source, it can create a charged pion. This pion will then decay, producing, among other things, a muon and a neutrino. The muon will decay further, producing an electron and yet more neutrinos. Therefore, the detection of high-energy neutrinos from a particular direction is a virtual announcement that protons are being accelerated there. It is the smoking gun that confirms a source is a cosmic ray factory. The hunt for this correlation is the holy grail of the field. In 2018, Ice Cube took a monumental step forward. They announced the detection of a single, extremely high-energy neutrino, which they named Ice Cube 170922A. The alert went out and telescopes immediately searched its origin. They found a known blazar, a galaxy with a supermassive black hole shooting a jet directly at Earth, flaring brightly in gamma rays at that exact time and location. This was the first compelling evidence of a high-energy neutrino source, and by extension, a powerful candidate for a cosmic ray accelerator. This collaborative, multi-messenger future is now the driving force behind the next generation of observatories. Projects are no longer designed in isolation. The Pierre Auger Observatory, which detects cosmic rays, coordinates its observations with neutrino telescopes and gamma-ray satellites. Upcoming facilities like the Cherenkov Telescope Array for gamma rays and the planned Ice Cube Gen 2 for neutrinos are being built with this synergy as their core mission. They will create a global, interconnected nervous system for detecting cosmic violence, with each new signal refining the search for the others. We are moving from an era of isolated observation to one of cosmic conversation, where a whisper from a gravitational wave detector can trigger a chorus of responses from telescopes and particle detectors across the planet and in space. This is how we will finally move from statistical correlations and broad hotspots to definitive, pinpoint identifications. The Multimessenger approach is not just adding new tools, it is fundamentally changing the way we see the universe, weaving together separate threads of light, matter, and gravity to reveal the complete, magnificent tapestry of the cosmos. But this grand Multimessenger conversation is only as good as our ability to listen. And to hear the faintest whispers from the cosmos, we are building a new generation of ears. The future of cosmic ray science is being forged in the designs of colossal observatories that will push the boundaries of our vision further than ever before. These are not merely incremental upgrades, they are revolutionary leaps designed to catch the most elusive particles with a precision that was once the realm of science fiction. And in doing so, they promise to finally answer the century-old question, where do these powerful particles come from? Leading this charge is the Cherenkov Telescope Array, or CTA, an ambitious international project that represents the next evolutionary step in gamma-ray astronomy. Unlike its predecessors, which consisted of a handful of telescopes, the CTA will be a vast array of over 100 telescopes spread across 2 sites in the northern and southern hemispheres. This sprawling network will act like a single, gigantic eye with unprecedented resolution. By using multiple telescope sizes, large ones to catch the faintest, lowest energy gamma rays, and small ones to capture the brief, intense flashes of the highest energy ones, the CTA will have a sensitivity 10 times greater than any current instrument. This means it will see fainter sources, resolve finer details within extended sources like supernova remnants, and detect phenomena that are currently completely invisible to us. For cosmic ray science, this is a game changer. By mapping the gamma-ray glow from proton collisions with exquisite detail, the CTA will effectively allow us to image the cosmic ray accelerators themselves, tracing the distribution of particles within a supernova shock wave or active galactic jet, and finally understanding the mechanics of these natural particle colliders. While the CTA will peer into the very high-energy universe, other observatories are aiming for the extreme, the truly unimaginable energies of particles like the Oh My God and Amaterasu events. The Southern Wide Field Gamma Ray Observatory, or SWGO, is one such project. Planned for a high-altitude site in South America, SWGO will not use traditional telescopes. Instead, it will be a massive array of water tanks or scintillation detectors covering several square kilometers. Its goal is to detect the extensive air showers created by the most energetic gamma rays and cosmic rays with a wide field view of the sky that is simply impossible for more focused telescopes. This wide-angle perspective is crucial for creating a high-resolution map of the entire sky at the highest energies. SWGO, along with an upgraded Pierre Auger Observatory, will be able to collect these ultra-rare events in vastly greater numbers. With thousands of such detections instead of just a handful, the statistical significance of any anisotropy, like the Auger hotspot, will skyrocket. What is now a faint, blurry smudge on the sky could sharpen into a clear, defined point, finally allowing us to identify individual galaxies as confirmed sources of ultra-high-energy cosmic rays. Perhaps the most visionary concept on the drawing board is POMA, the probe of extreme multi-messenger astrophysics. This is not a ground-based observatory at all, but a proposed NAS, a mission consisting of 2 satellites flying in formation. POMA's ingenious design would allow it to observe the atmosphere from above, looking down for the faint ultraviolet fluorescence trails left by the most energetic cosmic ray air showers. This space-based vantage point gives it a huge advantage, an enormous field of view and the ability to see the entire atmosphere below it as its detector. POMA would have a collecting area far larger than any ground array could ever achieve, making it the ultimate hunter for the most extreme cosmic rays. Furthermore, it would be uniquely equipped to perform multi-messenger astronomy from space. The same satellites could be tasked to quickly slew and point their instruments at the source of a neutrino alert from ice cube or a gravitational wave signal from LIGO, observing the ultraviolet counterpart to these events. POMA represents the ultimate synthesis of the multi-messenger approach, a single platform designed to catch cosmic rays, neutrinos, and the light from the same cataclysm, building a complete picture of an event from start to finish. The data from these future observatories will do more than just find sources. It will open a window to new physics, the persistent mysteries we face today, the violation of the GZK cutoff, the muon puzzle in air showers, the nature of the positron excess are all potential signposts to phenomena beyond the standard model of particle physics. By collecting orders of magnitude more events with far better resolution, these new instruments will allow us to test our theories with a rigor that is impossible in human-built colliders. We could finally determine if ultra-high-energy cosmic rays are indeed protons or something more exotic. We could discover if their strange properties are due to unknown interactions in space or evidence of entirely new particles. Every unexplained anomaly is a potential doorway, and these next-generation detectors are the keys we are forging to unlock them. We stand on the brink of a new era, not just of discovery, but of fundamental understanding, where the universe's own accelerators will reveal secrets about the fabric of reality that we could never learn on our own. As we conclude our journey through these 25 enigmatic cosmic rays, it becomes powerfully clear that they represent far more than just a list of high-energy events. They are a testament to the universe's dynamic and deeply mysterious nature, a collection of cosmic postcards from the edge of known physics. From the oh my god particle that seemed to break the rules of intergalactic travel to the positron excess that might be our first whisper from the dark matter universe, each one of these messengers carries a story of creation and destruction on an almost unimaginable scale. They are not anomalies to be filed away, but vital clues in the greatest detective story ever told, a story written in the language of subatomic particles and spanning billions of light years. What these particles ultimately teach us is a profound lesson in cosmic humility. For every answer we find like connecting supernova remnants to the galactic cosmic ray population, a dozen new questions erupt from the data. The universe is not a static museum to be catalogued, but a living, breathing, and violently energetic arena where black holes devour matter, neutron stars collide, and galaxies erupt in furious bursts of star formation. The cosmic rays we detect are the tangible shrapnel from these battles, the direct physical evidence that these events are not just pretty pictures in a telescope, but engines that fundamentally shape the composition and energy of the cosmos. Each time a detector on Earth registers one of these rare high-energy events, we are not just collecting data, we are sampling a piece of a distant cataclysm, and in doing so, we are brought one step closer to understanding the life cycle of matter and energy itself. This journey of discovery is accelerating at an incredible pace, driven by a new era of multi-messenger astronomy and next-generation observatories. The path forward is brighter than ever, with projects like the Cherenkov Telescope Array and POMA set to open new windows into the high-energy universe, offering clarity where we now see only blurry statistical hints. The next great revelation, the one that finally ties a cosmic ray definitively to its source or unlocks the secret of dark matter, could be made tomorrow. And this is why your curiosity is so vital. This isn't a story for scientists alone. It's a human story about our place in a vast and often bewildering cosmos. Every time we look up at a seemingly static night sky, we now know it is alive with an invisible rain of messengers, each one a potential key to a deeper truth. The quest to decode these cosmic rays is a continuous, unfolding narrative, and you have a front row seat. We encourage you to stay engaged and follow along as these discoveries are made. Which of these 25 mysteries do you find the most compelling? Is it the utter defiance of the Amaterasu Particle, or the tantalizing dark matter hints from the positron excess? Share your thoughts and questions in the comments below. We love diving into these discussions with you. And if you want to join us for the next big discovery, be sure to subscribe and hit the notification bell for more deep dives into the wonders of space. The cosmic conversation is just getting started, and the next message from the universe could be the one that changes everything.